Hello, everyone, and welcome to the United Nations University Institute for Water, Environment, and Health Science Talk series in this, our 30th anniversary year. I am Abraham Numbogo, and I'm delighted to be your host for today's Science Talk. For those of you who are joining us for the first time, our Science Talk series showcases the diverse policy relevant and interdisciplinary research of UNU-INWEH and a global network of experts. These sessions are designed not only to share cutting-edge science, but also to explore how science translates into real-world solutions for water, environment, and health challenges across the globe. Today's sessions, like all our talks, is being recorded. The video will be made available in an open access format following the event. And you can find recording of all previous science talks on demand via our website and YouTube channel at unu.edu/INWEH/science talks. As always, we will conclude with an interactive Q&A session. Please feel free to post your questions in the chat at any point during the presentation. Today's science talk is entitled Toward Reliable and Scalable Flood Mapping, Transforming Flood Prediction and Physics-Guided AI. And it is my pleasure to introduce today's speaker, Dr. Leila Hashimi-Beni. Dr. Beni's work focuses on advancing geospatial and Earth observation technologies to support environmental management, evidence-based decision-making, climate adaptation, and sustainability. At UNU-INWEH, Dr. Beni contributes to efforts in advancing geospatial analytics and remote sensing, applying AI and machine learning to address water-related environmental challenges, such as flood, water quality, and land use change. Dr. Beni is an associate professor of geospatial and remote sensing in the Department of Built Environment at the College of Science and Technology at North Carolina Agricultural and Technological State University. She has served as principal investigator or co-principal investigator on numerous projects funded by the NASA and the U.S. National Science Foundation, among others. It is my great pleasure to introduce Dr. Beni. Dr. Beni, the floor is yours.
Thank you, Dr. Ibrahim, for the introduction. It's a real pleasure to be here, and thank you for the opportunity to talk about the flood mapping that is an important tool for understanding and managing flood risks. Before getting into the technical side, I want to start with a simple point. Flooding is not a local problem. It's a global crisis, and basically it affecting very different regions in a very different way. For example, in Pakistan, a massive flooding impacted a large part of the country in 2022 that damaged crops, infrastructure, and millions of homes. That wasn't just a natural disaster, it became a large humanitarian and economic crisis. So in Libya, in 2023, two aging dams failed during Storm Daniel, and a wall of water moved through the city within hours, that wiping out entire neighborhoods. And that showed us that how multiple risk factors can be combined and create this disaster. But also, if we look at some well-prepared areas like in Germany, in Belgium in 2021, it shows us that even in this well-prepared area, still they are vulnerable when it comes to flooding. And that basically emphasizes and reminds us that we need coordination and timely information. We saw also the different flooding in Houston, Texas in 2017 during Hurricane Harvey, when the city received over 60 inches of the rain in just a few days, and that created a huge flooding. But what was surprising that many of the affected area were not even in the high risk flood zone. So all these cases basically have a clear message that it's important that we understand and manage flood risk. So these are only a few examples of flooding, but if we zoom out and we can see a clear global pattern over the past 4 decades, as we see in this picture, flood-related economy loses basically significantly increased. So that is not just because we have more extreme event we have, but is not the only reason. That the reason, another reason is because more people and infrastructure are exposed. So this is why the impact of any flood today is much bigger than in past. So that is why improving how we map, we predict flood risk is become very essential to us. So flood map basically enable critical decision for emergency responses, how we direct rescue team to high risk zone first, for damage assessment, for evacuation planning, and also for prioritizing resource allocation. Without having a reliable and timely uh, flood map, is even well-resourced response system, they flying behind. And also that important geospatial data is a backbone for any life-saving decision. When it's come to the flooding and predicting a flood, reliability is very important. When our flood map, we have false positive, that means there is no flood, but our system detect it as flood. It basically lead to unnecessary emergency response, and also we're going to use resources for the area that they are not really needed. But this becomes very important and concerning when it comes to false negative. That means there is flood, but we were not able to predict or map this correctly. That is when our people and property are left exposed. So in real situation, this is the case when communities receive no warning before basically a life-threatening flood event. For having an operational flood mapping system, we have to balance between three competing demands: accuracy, speed, and scalability. The system should be able to map the flooding and predict flooding in the different diverse condition, different urban area, land use, land cover. It should be fast enough for the for responder for flood management and also recovery. And also it should be scalable. If our data change or for the different environmental situation, that should work. Most of existing approach try to basically optimize their method for one or two, but achieving three of them is very challenging and still is one of those main research in flood prediction and mapping. So when we want to develop a method for flood prediction and mapping, maybe like we can think of three fundamental approach. Either physics-based method that basically is based on the water flow rules and physical behavior of the system, based on the data-driven, where observation and data is basically the core of the development and mapping. And when also we can combine these two methods together and create a system that work for like combine both data and also physical rule. So each of these methods developed based on the strength and also addressing some weakness of the others, and all try to move toward a reliable, understandable, and deployable flood mapping system. If we look at quickly at the different methods in physical-based model, basically start with our fundamental understanding of the physical system, how hydrological or hydrodynamic process work. And based on that, we come up with some event that we want to detect and or generate some hypotheses around them. We develop methodology and then we collect the data either from field or collect from remote sensing data, topography, or other information. We basically create a correlation between the observation and variables, and just we see that how we model the system. These physics-based models are very strong because it's come from our understanding about the physical system. But the problem is that this model normally simplify the physical system. They don't capture all variable in the complex system like hydrology or basically our water rule. So for this reason, that still we can't really use that for the real-time or near real-time situation, like for flood management and recovery. And sometimes also another weakness, creating a robust model is computationally expensive and also taking time. It's working based on the trial and test error, and then for this reason it takes time and it's go to iteration until we can come with the one solid and robust model. This is the one of the very simple physics model in remote sensing. So that normally we use the normalized difference water indices or we have different water indices that can quickly detect water, but it's very simple. That work with the electromagnetic spectrum and the water signature in that spectrum, that normally water strongly absorb the infrared signal but reflect the green light. So that easily can identify where we have water coverage. So this is an image that comes from NASA that is showing the flooding in 2020 around the Red River in Minnesota and North Dakota in United States. And in comparison with this imagery that both are from the Landsat 8, showing the area in the normal condition. And this is the quick flood planning using NDWI that basically extract the water area. That is very fast, can be used as the first step, but the issue is that when we have shadow, we have different land use and land cover, and when we have the noisy data, these methods are not really accurate. Sometimes they overestimate water, and sometimes also they have false negative. They can detect the flooding and kind of confusing the different landscape. So since last decade, maybe like data-driven approach become one of those main approach for developing flood mapping method. That's because we have a lot of data available. So these methods work is they are even based on machine learning or from the deep learning approach. In machine learning approach, for example, is here. Data, basically, we have the data through the feature engineering and also based on some statistical model, we can find some pattern, like for example, for flooding through the historical floods. And then it can basically find the different pattern and also connection between the different variables that those might miss in the physical model, and then basically predict the flooding for the new data set if they have those patterns as well. So this method seems very promising, but the problem is they are the data hungry approach. So they need a lot of the data. And when we have a lot of platform and a lot of remote sensing available, so using data-driven approach makes sense, especially deep learning. So we have many satellites that continuously observe our Earth, land border, and also we have a lot of the data from the airborne that is available to us. And we can also, even there are so many UAV data set available, and also ourselves we can collect the UAV data quickly on demand. We have a lot of sensor, in-situ sensor and measurement. So all of this data basically help we can have the, we can establish a data-driven method quickly. So regardless of the platform, we have also many sensors that working within the different electromagnetic spectrum. From we have imaging sensor, non-imaging. They can collect optical data, SAR, thermal, altimeter, radiometer, and spectrometer, for example. All of this data basically capture a specific characteristic of the water. So if we have all of them and we can combine them, fuse them, we can create a novel view and comprehensive and detailed knowledge based on the environmental dynamic, like for the rapid changing event like flood, like for flood mapping, and also for impact, how the erosion happen after flooding, or like for drought or some other basically process. So regarding those approach, we started to kind of develop some method for that our study area were in North Carolina because the data were available to us. Our study area was Lamberton during Hurricane Florence and Princeville during Hurricane Matthew. So these two areas are flood-prone area and experienced many flood during kind of since last decade. So the data that we used for flood mapping was LiDAR data and also high-resolution UAV data, both collected by North Carolina Emergency Management. And also we use flood gauge reading data that we normally use that for validation and also development as well. Here is some quick result. For this study area, we verify different approach from the simple remote physics-based model in remote sensing NDWI to machine learning, that random forest and SVM, and many also well applied deep learning approach. So as you see that in general, deep learning model achieve better accuracy for flood mapping. Here is some kind of the result that this is our test image in Lamberton during Hurricane Florence. This is the automosaic that combined from maybe 2000 UAV imagery. And this also is the result from the deep learning that's showing all of the blue show, dark blue is the flood area. And as you see that we have flooded and non-flooded, we had that segmentation, flood and non-flood, and also vegetation area, vegetated area. As first glance, the result looks very promising because we could basically capture all of the flooded area, open water area. But the issue was what happened in vegetation or in vegetated area. If they are flooded inundated vegetation or is just dry. This is very important for some area like North Carolina that sometime after extreme weather and hurricane, unseen water come to the city from these areas. So this is very important to know what's going on in those areas. For that, we also developed a method to combine that are basically data-driven approach with the topography. Here is a raster DEM, digital elevation model, that's showing that each pixel has the value for the elevation. If we have a gauge station and the reading is, for example, 43 here, so we can search the area around it. If the pixel has the basically elevation bigger than, larger than 43 here, this is the dry pixel. And another pixel that is 42 is the wet pixel. So based on that, we search in the area, and that's called region growing approach, that by it we can create quickly a flood map using only with the digital train model. But what we have done, we use that method, create a flood map using the region growing, and then we use a decision tree that if it's flood open water, use our data-driven approach. That flood map come from the deep learning, and if it's vegetated area, use that region growing. So region growing is the fast and effective, but the quality is directly depend on the quality of the topography data that we have. So it's not best approach, but at least give us some insight about that if it's the inundated vegetation or not. So this is the result of this approach. First one is the orthomosaic of the UAV data in Princeville during the flooding in 2016. And this is the validation in basically flood map from the USGS. And this is based on the deep learning flood map based on the deep learning, and this is the region growing flood map. So when we combine these two, we take the open water, basically the data from the deep learning and also the data from the inundated vegetation from the region growing. This is the final result. This actually for us was it's very promising. The reason because it's very is more similar to what is the validation flood map from USGS, but with this difference that this map created maybe like during months, but this image basic flood map was created during like 3 hours. So that basically minimized the creating the some data that help first responder and decision maker for flood management and recovery, and they don't need to wait for months until to understand what's happening in the area. So, and for the creating the third dimension of the flood map, we use the pre-flood DTN, and we overlay that our flood map in 2 dimensions on top of it, and basically it could give us the flood depth in each point in the area. Based on this result, we continue the flood map mapping using another support from NOAA that we try to, instead of using the topography map that for region growing that wasn't really reliable, just because the accuracy of topography is not really good everywhere, and sometimes it's not available. So for this reason, we started to work on the data fusion between optical and SAR. That SAR sensor is very promising for the flood mapping, especially during the kind of when we have a thick cloud cover or during night when optical sensor can't capture any data. So for that, we work on an infrastructure that our North Carolina Emergency Management collected UAV data that our collaborator in Socorro, basically, they try to do quick pre-processing, like georeferencing and sending to our database. And we also, in the cloud computing interface of the Google Earth engine, so we develop our method there, and then the result that was flood map and all of the shape file and raster basically go back to the Socorro website and be available to our NOAA partners. So here, that is basically the flowchart workflow for the image data fusion. We had Sentinel-1 and Sentinel-2, that optical and SAR and optical data. We try to combine them to the machine learning and also deep learning and create flood map. So for the machine learning, we tried the different approach. And so we first the data went through pre-processing, and then to the segmentation, we created a flood map, and then we did some post-processing to basically remove some noises and some, like the some unwanted data over there and just create the clean data. So here is the result from machine learning in Google Earth Engine. As you see that we use the different approach from random forest, but you see that this is the SAR data, VV polarization, VH polarization for SAR, and also this is the UAV data, so Sentinel data for the RGB, that is Sentinel-2. So as you see that all of those blue is kind of the open flooded area, you see that we got different results using the different method. This is because in machine learning, we do a lot of feature engineering. We have a still human intervention. So that basically based on each method, we might come up with a different result and see that is not really reliable to use machine learning directly for the flood mapping. For that, we develop data fusion through the deep learning approach that basically we provided more data, and the deep learning automatically create the correlation and extract the pattern in the data from the historical flooding, and then use that pattern for predicting and also the flooding in the new and unseen data. So here is some result that we had. Optical data, this is the ground truth. So that means manually labeled to make sure that there is our inundated vegetation, dry vegetation, open water, and we put all other feature in them as other because they were not the focus on this research. And if we look at the result from just using the optical data from UAV, from the Sentinel, like UAV and SAR, and fusion of the Sentinel with the UAV, different resolution, we getting the very good promising result from when we come fusing the UAV and SAR data. But during this study, we also noticed that we trained our model using the flooding from Hurricane Florence, but applied in kind of for Hurricane Matthew. But we noticed that really the accuracy reduced. So that means still deep learning has problem with the generalizability, and we can easily transfer the model to other area because the environmental condition in each area are different. So even data-driven approaches, especially deep learning, are very promising and they have a lot of potential. They come with the key challenges. Maybe like three of important of them are the data scarcity. When we have limited, high quality data are very limited, and also they are very expensive. Manual labeling of them is very time consuming and also error prone approach. And also we have another issue with multi-resolution data during flooding and any natural disaster. There is no guarantee that we have satellite data at that time. So sometimes we get the data from the different sources, is multi-source, multimodal data, that some are the coarse data that they don't have enough details, some are very high resolution data that is processing them is very time consuming. So one of the issue is how to fuse them, how we can get them, like a system that can get those data and create a reliable flood map for us. Another issue that also is very tricky is multi-temporal data, that most of the time we have a lot of missing data for flood mapping. So it's kind of satellite doesn't provide, like high temporal resolution, and sometimes we have different data that like we try to fuse two different data that we are happy we got the SAR data and optical data during one day, but maybe for some fast changing event like flooding, this is not a good case. The reason because flooding from morning to evening can change hugely, right? So this is the reason that this multi-temporal data is very challenging when it comes to the flood prediction and flood mapping. To address some of these issues, we have worked on developing the new data set for the flood mapping. So we can go with the high resolution imagery like UAV data and create, like some label data that can be used easily for the satellite imagery that they have lower resolution. So here we use the UAV data from the like also in addition to from UAV data is fed to the deep learning approach. Through unsupervised classification, we created like we segmented imagery, and then we classified them and then aggregate them and did quality control and finally created final flood mask that can be used as the training data set for the deep learning. So based on that, we introduced and we developed a deep flood that is published and is open access for every researcher that they want to use. That is the data come from, in addition to UAV, also we have satellite imagery, Sentinel-1 and 2 UAV data, and also UAV SAR from NASA that we label them, and from the 6 different flood-prone area in North Carolina. So that is just to help to our deep learning become more generalizable and work for different environmental conditions. So another data that also was developed for North Carolina is inundation to depth. And that is we develop a approach, like data set that has 3D, the annotated in 3 dimensions. So it has water extent plus depth. So that also the focus is for the urban area. So that also we use we develop the data for the 6 different flood-prone area in North Carolina that has kind of flood depth with it. These also all of the flood depth compared with the hydrological model, the depth that come from hydrological model, and also the high water uh, high level water mark, and also gauge station to make sure that data is has good quality. So for the addressing the low resolution data, we developed the super resolution approach that taking the low resolution data and convert to the higher resolution data and keeping some detail from that. So that is the Sentinel-2 that we converted to, we basically resampled to the that from 10-meter resolution to 5-meter resolution, but still you see that quality even is better. And we compared that result with the resampled UAV from the UAV data original resolution was 30 centimeter, but also we resampled to 5-meter to compare these two. And so we applied for the different basically land use, land cover, just see the quality, how we can basically improve the quality. And this address for multi-resolution fusion, when we have UAV data and we have satellite imagery and we have data from the other sources, we want to combine and bring them to an optimal resolution. Maybe like super resolution approach is one of those methods that can help. One of the other deep learning approach that very helpful for flood mapping is GANs. When we use that for the addressing couple issue. First one is the optical imagery is very user-friendly for the first responder. They can see the imagery and like understand that very well. But SAR data, because of the it captured the data in like radar band of the electromagnetic, is not easy to understand and normally it's very noisy. Sometimes when we have the flooding, it's happening when we don't have any earth observation, or it's happening during night when optical sensor can't capture the data. So if we find a way to translate the image together to each other, like for example, if we have SAR data, we can create optical data directly from it. It would be very helpful. So that can be done by GAN. That approach basically we try to reconstruct optical data using SAR data. So this is the some result that we have. This is the SAR VV polarization, VH. This is the targeted optical, and this is the what we received after applying GAN sensor, GAN basically approach. So this is very helpful. If we don't have any target, basically optical data, we have SAR data, we can quickly convert to the optical data. And that is very helpful, especially when we have a lot of deep learning approach that work with optical sensors. So that can fit to those approach and create flood map quickly for us, or at least first responder can see a better kind of and understand the picture very well during the disaster. And another, with all of those potential that deep learning has, it comes with many different issues, especially when data is incomplete and the quality is not good. So for this reason, maybe like deep learning, physics-informed deep learning or physics-informed AI is the basically coming. So in the physics inform, basically the prediction is done by the deep learning. We predict flood using deep learning, but considering some physical constraint, we can improve reliability. So that physical constraint can help to basically consider all diverse train type and land use land cover that improve our flood map accuracy. It can help with the transferability, like we generalize that our data to new area when without needing to retrain whole model again, and also help with the robustness that normally is stable, and especially if we have noisy data or incomplete data set, that physical rule can basically help the training of the deep learning approach and create better results. This is the workflow for deep learning for physics-informed approach that we implemented. For flood mapping, we use soil data and some topography data, and this is mask that is from the historical flooding that fed to the Apple, basically deep learning for training and prediction. So these data go through some pre-processing just to making sure that they are aligned, the resolution, everything is aligned, and then it's fed to the deep learning. It creates some prediction for flooded area. And this prediction is basically compared against, checked against some physical rule. Here is continuity and momentum. And then that basically comparison go to the physics laws, and that helping the improving training for our deep learning model. So if you want to see some of the results from this approach, we train that model using the open source data set that calls SEN1 Flood 11 that developed in 2020, and it's for 6 continents and 11 different flooding and different countries. So we use 80% for training data for training process. That means basically we try to make our deep learning very generalizable, and then we tested using 20% that never used for training. This is the unseen data. So this is the result. This is the SAR data. This is ground truth. What was the flooded area? And this is baseline, means AI, just deep learning alone. And this is the physics-informed prediction. So this is from the different flooding event in different country and different time. As you see that some of those area, we have some false negative in the data driven by, but that was able to improve using the physical informed deep learning, or we can see that in different area. So how the results change, and the flood map from this prediction is more reliable. So this is the other some other result from Ghana, India, and USA. You see that the different basically flood prediction using the this is the ground truth, this is AI, this is the physics-informed AI. So you see that this prediction is very similar to ground truth, and that improve reliability. Especially in this case, you see that the whole area was considered as flooded area, but with the physics, by adding physical constraint, we could improve the quality and reliability. So this is another example for when we don't have imagery, just we have the rainfall data, that using the physics-informed, just with two maybe simple constraint for monotonicity and also flood threshold constraint, we could basically address the flood prediction in data scarce basin. Here, this is the loss function that works with physical information. And here is the result. We see that we have like the baseline is the AI is blue and physics inform is in red. As we see that we have a lot of noises in the kind of AI approach, but physics inform approach improves that. So just because of the timing, I'm a little bit summarize the thing is that we have some, in this case, we have baseline limitation. So that our approach LSTM, that is the deep learning model, collapsed in the area that we had missing data. Also, we try and test the method, and we noticed that with the physics inform, we can have a stable prediction even with up to 80% missing data that is happening here. And the interesting thing about physics inform that always we can, through the physics, basically loss function and considering all of those physics rules, we can have the fallback mechanism that help to improve the training for the data-driven approach. And final results show that we could reduce 31.1% of the error when we just using the AI approach. And you just use two constraints, and even with minimal physics equalization, we could basically receive the very stable result for the flood mapping. So with all of the advancement in the deep learning and physics informed approach, we need to see how we can make it usable by everyone. So this physics informed approach is very promising for everywhere, especially for those regions that they have they don't have enough hydrological record or gauge station, or they don't have enough observation, especially for population that they experiencing the very frequent flood events, and also communities that historical left out from the disaster preparedness system. So that that means that technical excellence is not enough to get this method or get this tool used. So when it's come to deploying in the real world, there are many other considerations. We need to navigate challenges around data, infrastructure, trust, and integration of all of those in the workflow. So that means always any technology we develop, at the end we need to work with the end user to basically co-design that with the policymaker or with the first responder communities. So to make sure that we can make those basically science and technology available to everyone, and those that need and improve the warning system before any disaster. So we, if we have flood map, all of those flood map can be combined with other information, like from social media, from the other data set, socio-economic data set, and then we can go to the different use cases, analyze them, and provide the useful information for community for flood management and recovery. So we developed that for flood mapping, but we are also working on similar approach for addressing other environmental issue, for the smart and precision agriculture, for transportation. Especially we trying to combine transportation model with the flood mapping for the evacuation and planning, and developing a system that help community to evacuate, to identify shelter, and also and all of those flood mapping is the huge basically information, useful information for that system. And also we are working on the landslide prediction and mapping. We identify the damages and for prioritizing the allocation of the resource. and for the earthquake monitoring and also water quality assessment. So all of those methods that is developed is helpful for many other also application as well. So at this point, just I want to acknowledge and thank you all of my team from postdoc and to graduate and undergraduate students that contributed to this research and make this possible. Same thing also, I want to appreciate all of those funding organization and state and federal agencies that help from the funding, collecting data, providing the input to the, and also basically validating the research. I appreciate your time, so I would be happy to take any question.
Thank you so much, Dr. Benny, for the insightful presentation. We'll now move to the Q&A session. So I'd like to start the conversation by asking if we could clarify. You mentioned health data, and last week in our science talk, we learned that social markers like poverty and crime shape the patterns for wildfires. So I would like to know, besides the physical data that your model uses, could you clarify how social markers like poverty, human behaviors, then maybe political decisions also shape the patterns for floods?
Yes, thank you for this good question. Actually, any disaster, either natural or man-made, all of them come from the different factors. And our focus was more kind of developing machine learning and data-driven approach. And definitely what you mentioned, having, poverty, like because all of the social economic, I assume that they are also a main factor how we use our environment, right? So they are very important too, but at this point we have not kind of done. We didn't incorporate those factors because the even kind of using the multi-resolution data from the imagery alone has been a challenge for us. So, but definitely that is the very important question, and that what we can do at this point. And also what we are going with this research is going to move forward the impact and by overlaying the flood map, flood map from the different area and combining or in GIS overlaying the different social economy factor from the like the income, like just from the different factor we can come up, and using the machine learning or deep learning and see that how like from different events, those factors are very important. But definitely this is something that we're going to keep in mind when we are developing this research, and it's very important.
Thank you so much. From our online audience, GL asked, what's loss function? What hydrologic parameters or variables are used in ML training?
Yes, actually, we use that momentum and continuity. And if I want address basically accurately, just here is what like we use for the basically training. We use the precipitation in the time, and we use the, like the physical constraint that increasing precipitation shouldn't decrease discharge. And also we use the threshold constraint for that. That also we try to see that the extreme rainfall should produce high discharge. So this is the all parameter, but just when we use just deep learning approach without having this constraint, we notice that really sometimes we have the water flow like inverse, instead of going to the steep area, it's going to be upstream. So these physics constraints basically help to train them, kind of to check the prediction and help with the improved training and kind of improving the hyperparameter, like values for that prediction.
Okay, thank you.
Thank you, Dr. Benny. It's a very nice presentation, and then it's the approach of combining physics-based and deep learning is, I think, is a new way to look into flood mapping. My question is, how intensive this method in terms of computational and then also data access for scaling up? What are the major hurdles that you face, you envision to scale up this for a larger area?
Thank you, Dr. Martin. That is a very good question. Actually, in terms of the data, we have a lot of data available. Like we have over 800 observation satellites capturing data continuously from the Earth. So a lot of the data is collected by UAV with the airborne, with the, like UAV SAR, and recently also we have INSAR, basically sensor that really make like the flood mapping much easier. We have a lot of data, but the problem is the issue with the label data, annotated data. And this is where if we just want to go toward the data-driven approach, the model should have enough data to use as training. So we need to cover basically all different scenario, land use, land cover, like just different spatial temporal, like it need to learn. So if they get an unseen data, it can create a reliable prediction. So in terms of the raw data, we have a lot of data, and data-driven approach are very promising. But the issue is with the label data that make kind of those data-driven approach functional. In terms of the computational efforts, normally we need, definitely processing the satellite imagery using, we need to have a lot of GPU, like just we work with, for example, Microsoft using the Azure. We had access to, high-end GPU that wasn't able, we couldn't do that with our, like our computer because the data was really huge. But definitely that kind of computing resources is very important for the data-driven approach, but especially when we trying to predict flood in the huge area, and also its impact. Yes, I see that if we can address those basically computational resources, the data and also the label data, data-driven approach is very promising. But again, that doesn't mean that community is going to use that, because we need to always, like work with the decision maker and the end user to make sure that what they need, like we can, they can use those approach as well. But in general, I feel that these methods are maybe the only method for, at this point, for moving forward with the reliable and also quick flood mapping approach.
I just want to flag the fact that, thanks for the presentation. I just want to flag the fact that these are good point designs and initiatives like this that start now. It's one of the critical time to integrate all the factors that we are aware of. I understand the place of funding, money, cost and all those. But what do you think missing out on integrating the social issues that my colleague raised the other time, right from the start of an initiative like this?
Yes, the question is about that if we consider we adding more social factors for as input for deep learning approach or for after.
As input,
Yes.
right from the beginning, yes.
Yes, definitely. This is maybe what every of us want to do. Go to that way that we consider all of those factors from the technical input to all of those social economy. Like just poverty, for like just all of those factors as the input, and even more than that, considering like just the area, like the land use area, like the hospitals, like the area that people with dementia, like for example, living, all of them is helping to not only we map the flooding risk and also prioritize for the kind of recovery, right? So, and also for the management. Definitely this is the basically optimal system that consider all of them, but I feel like at this point we are at very early stage that we try to address those complexity with data itself to creating a system that can be functional, and then definitely when we are there, we can add more data. But what you mentioned is very important, and even we it's not important to map flood in the area that we don't have any community or we don't have any important infrastructure. So this is very important point that you raised. But I said at this point, I think most of the advancement is toward to make a flood mapping system functional for the data that we receive. And they look at that part for the community as impact. When we have flood map, so we can overlay the different factor on top of it, and then maybe like we can use all for different flood event, like poverty for different flood event, and then we can find even the maybe factors for creating the flood event and how also like the prioritizing the recovery for those areas as well.
Thank you, everyone, for joining our today's session. And many thanks to Dr. Leila Hashimi-Beni for this learning opportunity. We look forward to learning from you again in our future science talk. Thank you.
Thank you for the opportunity.